Welcome back to a new session of the MOOC on Information Security. Today we will see the details of the AES Cipher. The objectives of this module are to understand the various implementations of AES and to do an analysis of AES to get a thorough understanding of the algorithm. The AES. As we have seen in the previous session, the Advanced Encryption Standard or AES, also known by its original name Reindahl, is a specification for the encryption of electronic data established by the US National Institute of Standards and Technology NIST in 2001. As you are aware, AES is a variant of the Reindahl block cipher developed by two cryptographers, John Damon and Vincent Richman from Belgium. Reindahl is a family of ciphers with different key and block sizes. For AES, NIST selected three categories from the Reindahl family, each with a block size of 128 bits, but three different key length 128, 192 and 256 bits. AES is available in many different encryption packages and is the first and only publicly accessible cipher approved by the US National Security Agency NSA for top secret information when used in an NSA approved cryptographic module. The different AES parameters such as plain text block size, number of rounds, round key size and expanded key size depending on the key size is described here. For a key size of 128 bits, plain text block size is 128 bits, number of rounds is 10, round key size is 128 bits and expanded key size is 176 bits. And for 192 bits key size, plain text block size is 128 bits, number of rounds is 12, round key size is 128 itself and expanded key size is 208 bytes. And for a key size of 256 bits, the plain text block size is 128 bits, but the number of rounds is 14, round key size is 128 bits and the expanded key size is 240 bytes. Hope you can now recall the various transformation techniques used in AES such as byte substitution, shift rows, mix columns and add round key. In the byte substitution step, each byte in the state is replaced with its entry in a fixed 8-bit lookup table S such that B of ij equal to S of aj. In this step, each byte aij in the state array is replaced with a substitution byte bij using an 8-bit substitution box. Remember that before round 0, the state array is simply the plain text or input. This operation provides the non-linearity in the cipher. The S box used is derived from the multiplicative inverse over GF to raise to 8, known to have good non-linearity properties. In mathematics, a finite field or Galois field is a field that contains a finite number of elements. The Galois field is useful for cryptography because of the arithmetic properties helping scrambling and descrambling of data. This finite field is important in various cryptographic algorithms such as ECC, which we will explore in the coming sessions. To avoid attacks based on simple algebraic properties, the S box is constructed by combining the inverse function with an invertible affine transformation. Affine transformation is a method of mono-alphabetic substitution cipher where each letter in an alphabet is mapped to its numeric equivalent, encrypted using a simple mathematical function. The S box is also chosen to avoid any fixed points. While performing the decryption, the inverse is used, which requires first taking the inverse of the affine transformation and then finding the multiplicative inverse. In the shift row step, bytes in each row of the state are shifted cyclically to the left. The number of places each byte is shifted differs according to row. The shift row step operates on the rows of the state. It cyclically shifts the bytes in each row by a certain offset. For AES, the first row is left unchanged. Each byte of the second row is shifted one to the left. Similarly, the third and fourth rows are shifted by offsets of 2 and 3 respectively. In this way, each column of the output state of the shift row step is composed of bytes from each column of the input state. The importance of this step is to avoid the columns being encrypted independently, in which case AES would degenerate into 4 independent block ciphers. In the mixed column step, each column of the state is multiplied with a fixed polynomial. In the mixed column step, the 4 bytes of each column of the state are combined using an invertible linear transformation. The mixed column function takes 4 bytes as input and outputs 4 bytes, where each input byte affects all 4 output bytes. Together with shift rows, mixed columns provides diffusion in the cipher. During this operation, each column is transformed using a fixed matrix. Matrix multiplication is composed of multiplication and addition of the entries. Addition is simply XOR. If processed bit by bit, then after shifting, a conditional XOR with 1b16 should be performed if the shifted value is larger than FF to the base 16, which is the highest 2-bit hexadecimal value. In the add round key step, each byte of the state is combined with a byte of the round subkey using the XOR operation. In the add round key step, the subkey is combined with the state. For each round, a subkey is derived from the main key using Randall's key schedule. Each subkey is the same size as the state. The subkey is added by combining each byte of the state with the corresponding byte of the subkey using bitwise XOR. Cipher optimization. On systems with 32-bit or larger words, it is possible to speed up execution of this cipher by combining the sub-bytes and shift rows steps with the mixed column step by transforming them into a sequence of table lookups. This requires 4 256 entry 32-bit tables together occupying 4096 bytes. A round can then be performed with 16 table lookups operations and 12 32-bit exclusive OR operations, followed by 4 32-bit exclusive OR operations in the add round key step. Alternatively, the table lookup operation can be performed with a single 256 entry 32-bit table occupying 1024 bytes, followed by circular rotation operations. Using a byte-oriented approach, it is possible to combine the sub-bytes, shift rows and mixed column steps into a single round operation. Working of the cipher. It is already mentioned that AES performs operations on bytes of data rather than in bits. Since the block size is 128 bits, the cipher processes 128 bits or 16 bytes of the input data at a time. The number of rounds depends on the key length, as 128-bit key uses 10 rounds, 192-bit key uses 12 rounds and 256-bit key uses 14 rounds. Creation of round keys. A key schedule algorithm is used to calculate all the round keys from the key. So, the initial key is used to create many different round keys, which will be used in the corresponding round of the encryption. Encryption in AES. AES considers each block as a 16 byte, that is 4 byte by 4 byte equal to 128 grid in a column major arrangement. The arrangement will be like B0, B1, B2, B3 in the first column, then B4, B5, B6, B7 in the second column, etc. Each round comprises of 4 steps: byte substitution, shift rows, mixed columns and add round key. The last round does not have the mixed column round. The byte substitution does the substitution and shift rows and mixed column performs the permutation in the algorithm. After all these rounds, 128 bits of encrypted data is given back as output. This process is repeated until all the data to be encrypted undergoes this process. Decryption. The stages in the rounds can be easily undone as these stages have an opposite to it, which when performed reverts the changes. Each 128 blocks goes through the 10, 12 or 14 rounds depending on the key size. The stages of each round in decryption is as follows: add round key, inverse mix columns, shift rows, inverse byte substitution. The decryption process is the encryption process done in reverse, so it will be explained the steps with notable differences. Inverse mix columns. This step is similar to the mix column steps in encryption but differs in the metrics used to carry out the operation. Inverse subbytes. Inverse S-box is used as a lookup table and using which the bytes are substituted during decryption. AES instruction set is now integrated into the CPU, offers throughput of several GBs to improve the speed and security of applications that use AES for encryption and decryption. Even though it's been 20 years since its introduction, we have failed to break the AES algorithm as it is infeasible even with the current technology. Till date, the only vulnerability remains in the implementation of the algorithm. Hope you are clear with the implementation details of the AES algorithm. See you next time. Bye.